welcome you to another exciting statistical topic. We started this topic yesterday that I called distribution of discrete random variable. So we're actually going to continue from where we stopped. So this is titled distribution of discrete random variable part 2. Okay, so in the outline today, I'm actually going to review expectation and variance of random variable that we started yesterday. Then I'm also going to walk you through what I call linear combination then of random variables. Then from there, I'm going to introduce you to Bernoulli and binomial probability distributions. Okay, so like I said, I think what I'm four of us going to do is to walk you through the linear combination of random variable. Of course, you've been introduced to random variable, and you know by now that random variable is a mapping function that assign numerical values to elements in the sample space. Now, if I have a particular random variable that is also a function of another set of random variables, I'm talking about random variable y. It's also a function of another set of random variable x, like x1, x2 up to xn. And of course, the components, the x1 has a weight a1, x2 has a weight a2. So a1, a2 up to an, they are constants. They are acting like a weight, more or less talking about the contribution of each of those variables to y. That's what it means. Now, if I have a random variable y, okay, that's a linear combination. So what you are seeing now, the shortest way of writing that, instead of writing a1 x1 plus a2 s2 plus dot 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 until you get to an xn, we're basically going to write that as summation aixi, where I start from 1 to n, as you can see. Those of you online, can you confirm if you can see the lecture slide? Can somebody confirm by talking if you are seeing the lecture slide?
Yeah, we can see it.
Okay, thank you so much. Thank you for confirming that. Okay, so this is what we call linear combination of random variables. Now I'm going to go into theorem. Okay, theorem 3.1. Okay, if I have a particular random variable x, the mean of that exists. Okay, the mean of x is expected value of x, as you can see. So if a and b are constants, okay, the expected value of ax plus b or ax minus b, okay, so all what I'm just trying to say is I have the expectation of ax plus b, or I'm talking about expectation of this guy, okay, the expectation here, okay, we always attract a variable. A and b are constants, okay. Expectation of a constant is a constant. So this can actually be written as this. Okay, take a look at that. So what do you see? The expectation attracts just the variable, as you can see. The same thing is going to happen here. So where you're going to have this. Okay, so take a look at that. So that hold, okay, mathematically that hold. For example, you want to find the expected value of 2x minus 4. Expected value of 2x minus 4. So what I'm trying to say is going to be this guy. Okay, so where you need to know what is the that has to be given. The mean of x has to be given in order for you to be able to do that. Now, when a equal to 0, okay, just plug in a equal to 0. When a equal to 0, exactly that's what you're going to get. Okay, so and the expected value of b is going to be equal to b. Okay, so take a look at that. Okay, now if you take a look at the theorem 3.3 now, okay, we're just talking about the expectation of linear combination of random variables. Okay, the expectation of linear combination of random variables is basically going to be equal to what you are seeing. A1 expected value of x1, a plus a2 expected value of x2. So take a look at all of that. So what I'm trying to say in essence, so what I'm trying to say in essence is that expected value of a1 x1 plus a2 s2 until you get to an xn, okay, is the same as a1 expected value of x1, a2 expected value of x2. So until you get to an expected value of xn, that's exactly what we mean, because the a1 up to an, they are constants, okay, and I can actually rewrite that in a short form. If I want to write this guy in a short form, and that's why you're going to see summation ai xi, I start from 1 to n. Okay, so this guy is a shorter way to write this. Okay, so if I want to write this guy now, I'm actually going to do summation ai, okay, and the expected value of xi, okay, okay, where I start from 1 to n. Take a look at that. But that's a generalization. So remember that a1, a2, up to an are constants. And if you take a look at that corollary now, that is when I'm only focusing on two variables, x and y. Okay, I'm going to do expected value of x plus y. Expected value of the sum is equal to the sum of the unconditional mean. That's what it means. And the expected value of x minus y is just basically going to be expected value of x minus expected value of y. So take notes. Now, when you take a look at, when we talk about expectation, expectation means average. If you can talk about expectation of a linear combination of random variables, we can also talk about the variance. Okay, expectation is an average. How reliable is average? That what is going to tell us that story is basically going to be, um, the variance. How reliable is the average? So if I have a random variable x, the variance is sigma square x. The variance of x is going to be sigma square x. Okay. Now, if I now want to have a variance of a linear combination now, so if I want to have the variance of a linear combination, as you can see, I want to have the variance of ax plus b. Like I said, where a and b are constants. Okay, where a and b are constant. If you take a look at what I have here, I can rewrite this as variance of ax plus variance of b. Okay, now a and b, like I said, a and b are constants. Okay, now what is the variance of a constant? A constant doesn't change, right? The variance of a constant is going to be 0. This guy is 0. Then here, now when you have a constant inside a parenthesis, okay, that if that very constant comes out, it's going to be a squared variance of x. Take a look at that. A squared variance of x. Okay, an example of this, if I ask you to find the variance of 3x plus 9, the variance of 3x plus 9, okay, the variance, the 3 and 9 are constant here. If I want to rewrite this, I'm actually going to write this plus the variance of 9, and the variance of 9 is 0. Okay, a constant doesn't change. There's no variation when you talk about constant. That's why it's 0. And right here, I'm actually going to have 3 squared variance of x, which is going to be 9 variance of x. Okay, that's going to be 9 variance of x. That's what we have. So take a look at that. So that is what that guy is trying to talk about. If I have linear combination. I want to figure out the variance. Let me tell you this. What even if it is minus, if what I have here is minus, for instance, if what I have, if this guy, if what you have in the middle is minus, okay, you're actually going to have the variance of ax, okay, plus the variance of minus b. Take a look at that. Okay, now here, a squared variance of x. If you take a look at this guy, there's a minus 1 here, right? Okay, there is a minus 1. So if the minus 1 comes out, minus 1 squared variance of b, but the variance of cosine is 0, then I'm still going to have a squared variance of x. Does that make sense? Okay, so just to be able to show you all of that. Now we now want to generalize the variance from the linear combination now. Okay, if I have x1, x2 up to xn, they are independent. Okay, they are independent means the covariance equal to 0. If variables are independent, it means covariance. Covariance is you're talking about the joint variability. The joint variability will be equal to 0. Now we want to find the variance of a1 x1 plus a2 s2 up to that. Okay, so what I'm trying to say here. So what we're trying to say here is we want to find the variance of a1 x1 a2 s2 until you get to an xn. X1 up to xn, they are the random variables. A1 up to an are constants. And if we're told that x1 or s2 up to xn are independent, if x1, x2, xn are independent, it means they don't have relationship. Okay, so if I want to rewrite this guy now, okay, this guy is going to be equal to the variance of a1 x1 variance of a2 x2 until you get to variance of an xn, right? Okay, if you want to split that out, so the constant is going to come out. So I'm actually going to have this guy plus a2 squared variance of x2 until I get to an squared variance of xn. Okay, and you know what, I can rewrite this as a1 squared sigma. I can just do sigma 1 squared or sigma x1 squared a2 squared sigma x2 until I get to an squared or sigma sn. Take a look at that. So if I want to, that is exactly what you are saying on the board. If I want to write it in short form, when you take a look at this guy here in short form, okay, it's basically going to be variance summation ai xi I start from 1 to n. If you take a look at all this in short form, okay, now the generalization, now you can also write this guy in short form, what you're seeing on the board. Okay, so the short form of this guy now is basically going to be summation ai, okay, sigma xi squared I start from 1 to n. So this is in short form, the short form of all this. When I equal to 1, oh, sorry, that's going to be a squared. When I equal to 1, it's going to be a1 squared. I equal to 1, then you're going to have that. Take a look at that. That is a short form of writing all of that. So you need to be able to work, familiar yourself with all this notation. So now I'm going to go into corollary. If I'm now focusing on just two variables, x and y, and the x and y are independent, okay, then this condition holds, the variance of as plus by. This is just for two scenarios. This is for so many scenarios. When you take a look at what you see under corollary now, it's like focusing on the first two. Focusing on the first two. Take a look at that. So the variance into AX plus BY is going to be that. AX minus BY also going to be that. What did you notice? The variance into AX plus BY and variance into AX minus BY will give the same expression. Then the variance of X plus Y is that of variance of X minus Y. So what I mean by that is like the third one, the third in the corollary. The variance of X plus Y equal variance of X plus variance of Y. And the variance of X minus Y equal the same, equal variance of X plus. You may be wondering why that happened, right? I'm going to show you now. If you take a look at the one under corollary, I'm talking about the last two under corollary. Okay, if you take a look at, sorry, the last one under corollary, the variance of X plus Y equal variance of X plus variance of Y. Of course, we know that. Okay, variance of X plus variance of Y. Now, what about the variance of X minus Y? Let us look at this. So this is going to be variance of X plus the variance of negative Y, right? The variance of negative Y. There's a negative Y here, right? Okay, so if I want to rewrite this guy now, I'm going to write the variance of X plus, this is like negative 1 and Y, right? Negative 1 and Y is negative Y, right? Negative 1 is a constant. It's going to come out and become a square. Okay, so I'm actually going to have the variance of X plus, by the time this one, I'm actually going to have this one squared, variance of Y, and finally, I'm actually going to have the variance of X plus variance of Y, because negative 1 squared is just going to be a positive. Does that make sense? Okay, now that's all we have. Now from there, we can go to example. Okay, let X and Y be two independent random variables such that they've given you expected value of X to be 2, variance of X to be 4, and expected value of Y to be 7, variance of Y to be 1. And the question now, find the expectation into 3X plus 7, then find its variance. Whenever you figure out what the expectation is, then you also need to know what is the variance, because the variance tell us how reliable is the average value that you have. Now, I want to walk you through where you take a look at what you see now. When you take a look at what you see now, those of you online, I believe, can you see the board? I mean, the whiteboard,
Yes,
black.
yeah, we could
Oh, thank you
see.
so much. Thank you for confirming that. Now, you have expected value. You want to figure out the expected value of 3x plus 7. Okay. Now, what you're going to do first is going to be 3 expected value of x plus 7. Right? I told you expectation will grab variable. Expectation has affinity to grab variable. Why is the expectation? Now, even if I put expectation on 7, it's still going to be a 7. Expectation of a constant is a constant. Okay? You gotta know that. Now, you've been given expected value of x to be 2. All you just need to do is to plug that in, right? So it's going to be 3 into 2 plus 7. That's going to be what? 6 plus 7. So this is going to be, that's all. That is the mean. So the expected value of x has already been given. Take a look at that. Okay. Now, if you want to find the variance now, okay, the variance of 3x plus 7, okay, the variance of 3x plus 7 now, okay, like, when you want to, if I were you, you can save your time. Where there is no variable, you don't reckon with that. This is more or less the same as just variance of 3x. If there's no variable, there's no variation. I think you know that, right? No variable, no variation. Okay, now 3 here is a constant, right? So it's going to be what? 3 squared variance of x. So what is 3 squared? 9. What is the variance of x? Given. The variance of x is 4, right? Plug in 4. What is your variance now? 36. I'm done. The variance is 36. If the variance is 36, maybe the question, what of if they ask you to figure out? Now, for information, another way we can rewrite that is to write sigma squared 3s plus 7. See, variance is sigma squared. Of what? Of 3s plus 7. That's why you are seeing that. Does that make sense? There's like a notation for that. Okay. Now, what if they ask you to find the standard deviation? Maybe what it has to is this guy. Okay. The sigma, not sigma squared. All we're just going to do here is just going to do a square root of 36, which is going to be 6. Standard deviation is going to be the square root of the variance. Okay. Now, that was how we got all of that. You can also solve the second question. Is there anyone who need clarification on what I'm displaying now? Is there anyone who doesn't understand how to figure all that out? Is there anyone? Okay, so what we're doing now is actually the linear combination. It's like, finding the expectation and the variance of the linear combination of random variables. Okay, math is easy when you follow rules. Okay, the way you follow, you're basically going to be fine. Now, I want to go into more real life example on expectation and variance. The maximum patent life for a new drug is 17 years. Subtracting the length of time required by FDA for testing, okay? For those of you that are not in the United States, that are not based in the United States, maybe FDA is a Food, Drug, and Administration, okay? So, required by FDA for testing and approval of the drug provides the actual patent life for the drug, that is the length of time that the company has to recover research and development costs to make a profit. The distribution of the length of actual patent life for new drug is given below. Why is the distribution of that given? Because that is a random variable. Every random variable will have a probability distribution. And that is distributed like this, of course, you see. Yesterday, I actually walked you through how to construct a table like this, right? A table where you're going to have random variable with a corresponding probability. Now, this data has already been collected, okay, and the years actually go from 3 to 13. The 3 to 13 here is the support of y, support of random variable y, that we also call a state space. Possibility, the possible values of the random variable. And of course, you can see the corresponding probability. What does that mean? Make sense of that. Let's make sense of this particular data. What is the meaning of 0.03? 0.03, maybe like 3%. It means 3% of a time, 3% of a time. Okay, the years is 3. Okay, 3% of a time. Okay, 5% of the time is 4. 1% of a time is 13. I told you yesterday, probability is actually talking about frequency. It's trying, when you see a random variable having a different values for probability, it's trying to tell you it means the chance of occurring. Some random variable has greater chance of occurring than other. That's what it means. Otherwise, if they are equal, if the chance of occurring is equal, then you're actually in the probability, you're actually going to see equal values. Does that make sense? Okay. Now, in a situation like this, situation where you have a random variable and its corresponding probability, how do we figure out the average? We live in a world of average. We want to figure out the average. And that's why you see, find the mean patent life for a new drug. And the moment we get the average, how can we actually uh, you know, be confident that the value that we got for the average will represent the data set. And that's why we're going to go for either the variance or the standard deviation. You don't just need to do math. I need you to be able to understand, like, what is the essence of what you're doing. Why am I calculating that? So you, of course, we want to get a mean, and we cannot, if for we to tell how reliable is the mean, how can I trust my mean? Then I need a standard deviation. Okay, look at another question. What is the probability that the values of y falls in the interval mu plus or minus 2 sigma? Okay, that is like within 2 standard deviation. It means I need to first figure out what is my mean, which I've done in A. Mu is the mean, which I've done in A. Sigma is the standard deviation, which I've done in B. Then I'm just going to compute that. Let's see. Let's see how it works. Now, if you want to figure out the mean, the expected value of y, of course, I showed you yesterday. If you want to find the mean, all what you just need to do, you need to multiply the value of the random variable by corresponding probability. Then you're going to add them up. So what I'm trying to tell the world now is this. Mu is this expected value of y for a discrete random variable. It is summation y, the probability of y. Okay, so if I have y I start from 1 to how many situation here? Okay, 3 to 13. You can actually, you can do this. You can just do this. You can say, okay, you can say y start from 3 and ended up in what? In 13. Let me see, 3, 4, 5, 6, 7, 8, 9, 10. Yep, that's what. So this is a generalization. So take a look at that. That's exactly what we're doing here. That's what we're doing here. Just using the probability. Use it to multiply the outcome. Then you sum that up. Then the mean is 7.9. Okay. So so how can we interpret that? The required mean patent life for a new drug is 7.90. Now, do you know that it is not all patients that will experience 7.90? Some patients will have their own to be less than 7.90. Some we have their own to be more than 7.90. And if I now want to know, okay, how far apart, I want to talk about on average the distance of 7.90 to other respective observation, then I need a standard deviation. You know, this is what I used to tell my professor. Don't you have to tell me the reason. When you are telling me this, what is the reason? Or if your professor doesn't tell you that, figure out the reason why we're doing that. Now I don't just calculate a standard deviation. You want to find a standard deviation just because you really want to know how can you trust your mean? How far apart? Because if your mean is far away from the respective observation, then your mean cannot be trusted. But if your mean is very close, on average, okay, then your mean can be trusted. That's what I mean. That's what I mean. Now, right now, want to find the standard deviation? Of course, the standard deviation is the square root of the variance. Why not using just the variance? The reason why we're not using the variance, just the variance, is because of the fact that the variance is in a square unit. The unit of the mean and the unit of the variance are not the same. And therefore, the reason why we need standard deviation is for us to have, a metric of evaluation that will have the same unit as the mean. And if I want to remove the square in variance, what am I going to do? I'm just going to take the square root. The square root is going to take the square away. And that's exactly what I'm doing here. So if you want to find the variance, of course, like I said, you may not be able to get a standard deviation without passing through the variance. So what is the variance? Expected value of y squared minus expected value of y all squared. The two are not the same. What is the expected value of y squared? Expected value of y squared is going to say, okay, you know what? Before you use the outcome to multiply probability, make sure you square the outcome. That's why you say y squared p of y. Okay? Then the expected value of y, of course, is the mean that you've calculated before. You're just going to square that. Then in the end, you find the square root, you have 2.17. Is there anyone who doesn't understand how to figure out this, whether in person or online? Okay. Now, I want to go to the third question. Now, in a stochastic world, we we normally find probability. For instance, we've gotten the mean, we've gotten the standard deviation, and we actually want to know what would be the number of patients or the percentage of patients that we actually fall within the two standard deviation. And that's going to be 2 minus 2 plus or minus 2 sigma. I want to find the probability of that. If I want to find the probability of that, we're still going to do something that has to do with this in a continuous probability distribution, because the idea of a normal distribution will be used here. I don't know whether you've heard about z-score. Has anybody heard about z-score before? You've heard about that, right? Okay. Now the idea of a z-score is going to be used right here. So we want to find the probability of a mu minus 2 sigma. Y lie between mu minus 2 sigma and mu plus 2 sigma. If I want to do that, I need a z-score. The z-score is going to be that particular variable you are interested in minus the mean of that divided by the standard deviation. The variable we're interested in is mu minus 2 sigma and mu plus 2 sigma. Look at that. And what is the mean? The natural one. That was why we say minus mu. Okay, so what I'm trying to say is we're still going to do all of that, So, so we have a z is random variable minus mu over sigma. But the mu here, okay, this, let me use y. The y here, we actually say y lies between mu minus 2 sigma mu plus 2 sigma, and that is why here you're actually going to put this guy and also going to put that guy, and that was what led to all that. Okay, and in the end we're going to check from a normal table, which I'm still going to walk you through. Oh, go ahead. It's between -2 mu minus, when you, this is what actually happened. We want to find this, right? So this one means y lie between mu minus 2 sigma and mu plus 2 sigma. Do you see that now? So this is this random variable y is fall between this guy and this guy. So and I want to find the probability. Okay, to find the probability, we're going to make use of a z-score. We need to first of all standardize. What are we standardizing? Inside here, I'm going to put the upper one. I'm going to put the whole of this inside here. Minus, this is a natural mean for y. That is, what we just figure out. We just figure out that mean, right? Expected value of y is the mu for y. So before you can use a z-score, right, you need to first know this and this. Does that make sense? Okay, so I don't know if I've answered your question, right? Yeah, you can, of course, you can do that. Yeah, maybe I'm just wasting my time. I don't understand what you mean. What you mean? The 7.90 will cancel 7.90, which means mu cancel mu. But I was detailed here for students to be able to see. You understand what I mean? The detailed information. I get what you mean that, oh, mu can cancel mu out. In the end, that's what's going to happen. Okay? So which means in the end, you're going to have -2 sigma and +2 sigma because the mu which can cancel out. You are right. Okay, now I think that is how far we can go on that. Now, what we want to start now, we require some rigorous mathematical knowledge. If you don't have that prerequisite, I will advise that you listen and you focus on the board. Now, we want to talk about some special probability distributions. Just like the same way we have states, Midwest, Southeast, and stuff like that. We have some state in the Midwest. We're also going to have we have a discrete probability distribution, and one of them is what we call Bernoulli. Okay. Now, when I talk about Bernoulli, Bernoulli is more or less like a probability distribution that's used to model a trial that have two possible outcomes. You model a trial with two possible outcomes, just two. Okay, success or failure. The probability of success is going to be denoted as P, and the probability of failure is going to be denoted as 1 minus P, because success and failure are mutually exclusive. Now, when I have so many Bernoulli, then I'm going to have binomial. I just wanted to see the difference between Bernoulli distribution and binomial distribution. Bernoulli distribution and binomial distribution, they are characterized by two dichotomous outcomes. Do you know what I mean? Bernoulli versus binomial. The two of them, right, characterized by two possible outcomes, success or failure. Okay, sick or healthy, profit or loss. Okay, winning election, losing election. Does that make sense now? Okay, but the difference between the two, Bernoulli involve only one trial. You try once, but binomial more than once. Does that make sense? That is the difference between the two. Now, I needed to pay attention now. Okay, if a random variable x follow Bernoulli, we normally write it this way: BER with parameter p. What is the probability mass function? The probability mass function is basically going to be our p raised to power x. Okay, 1 minus p raised to power 1 minus x. Okay, s start from 0 to 1. This is a probability mass function for Bernoulli. Okay, this is a probability mass function for Bernoulli. X represents the number of successes. Okay, the number of successes here actually means the number of characteristics of interest. So this is Bernoulli. Now, the expected value, the mean, in every distribution, we basically need information about what is going to be the expected value of x and what is going to be the variance of x. For Bernoulli, it is P. I'm going to show you all of that. For the variance of that is P into 1 minus P. So in the case of Bernoulli distribution, the numbers of trial is 1. X represent the number of success. When I try once, it's either I record 0 success or 1 success. This is the state space of Bernoulli distribution. Now, I'm actually still going to derive all of this with you. Now, the next thing I basically want to do now, let's now go into binomial. Okay, for binomial distribution, x followed by okay, parameter n and p, okay, f of x equal n combination x, p raised to power x, 1 minus p raised to power n minus x, and the state space is going to be 0, 1, 2 until you get a hand. I need you to compare the two distribution. One is Bernoulli, the other one is binomial. But the two of them, okay, they used to model dichotomous outcome. The difference between the two distribution now, okay, for Bernoulli, the numbers of trial is 1. For binomial, okay, we have n numbers of trial. So right here, expected value of x equal to np, the variance of x equal np into 1 minus p. If you compare the mean and the variance of these two now, we're basically going to see that when I plug in n equal to 1, okay, when you plug in n equal to 1 here, okay, this is going to take us here. And that makes binomial to be a generalization of Bernoulli. Binomial is a generalization of Bernoulli. Why Bernoulli is a special form of binomial? Why Bernoulli is a special form of binomial? So that is what I'm trying to showcase right now. Okay, this is the properties of binomial distribution. Okay, you perform experiment repeatedly, and in each trial it could be success or failure. You have a coin, toss it so many times. It's either you see head or you see tail. That's what it means. Okay, what you're going to define as success is your characteristics of interest. I told you the other time, nobody goes into research with an empty mind. We have an assumption here: trials are independent. You don't depend on one another. And of course, we're actually focusing, we're interested in a particular random variable. Here I'm using X as a random variable. I can use Y as a random variable. Okay. Um, you know, like I said, I'm still going to derive all this because in theory of statistics, I need to show you how we derive this to be this. But I'm going to leave that for the next class. But what I want to do now is, what do we use binomial distribution to do? A very typical example of a binomial distribution is a medical trial. Okay, um, you know, if a clinical trial is conducted and participants were given new medication. Okay, how many of the participants given new medication actually will experience side effects? Because it's either this guy that received medication, it's either it has a side effect or not. That's binomial. Either this or that. That's what we mean by, you know, binomial and Bernoulli. They have two possible outcomes. Now, if from medical, let's say, if it is believed that five, suppose 5%, or if it is known that 5% of those who receive a drug, okay, we have side effects. Okay, now we can use binomial distribution to find the probability that if a random sample of, let's say, 20, okay, 20 participants, they were given the same drug, what is the probability that maybe more than 5 of them will develop the side effects? That is one of the applications of binomial distribution. Another application of binomial distribution is to look at the let me use example from the one you're going to like. Shopping returns. You know, some stores that sell items, okay, they normally experience situation whereby customers will return the item back to them. Okay, now if it is known that 10% of all orders, okay, are being returned in a week, we can use that idea. That 10% of order being returned in a week is P that we're talking about. P. That's what because the P here is the probability of success, the probability of the characteristics of interest. Okay, so if 10% of if it is known that 10% of all orders are being returned in a week in a store, okay, if 50 orders are made, we can use the probability distribution to figure out what is the probability that more than 10 orders will be returned, or less than 10, or between 5 and 10 orders will be returned. Of course, we need probability distribution to take decision in a stochastic world. What about talking about fraudulent transaction? Okay, if it is known that 5 or 2% of transaction involving credit card is fraudulent in a particular region, we may want to figure out maybe out of 50 transactions in a day in that particular region, what is the probability that more than 10 of that will be fraudulent? The probability distribution the binomial distribution can also be used. Now, take a look at this example. If 15 people are known to have contracted this disease, what is the probability that at least 10 survive, 3 to 8 survive, exactly 5 survive? Because if they can survive or not, that is dichotomous. Okay? Of course, I'm going to show you how you can use a formula and how we can use a table to figure that out. But what I'm going to quickly show you now is when I actually, because in binomial distribution, there are two parameters: the numbers of trials and the probability of success. Do you know that if I actually plot, yesterday we plotted, we constructed an histogram where we plotted probability of a random variable against the corresponding value of the random variable. If the numbers of trial equal to 10 and the probability is 0.1, the histogram we're going to have will be different from when if you take a look at the second one. When n equal to 10, p equal to 0.5, the difference between the first graph and the second graph is that the probability of success has increased. While the numbers of trial remain, look at the shape. The shape of the second one is looking like a shape of a normal distribution. We're still coming back to normal distribution. Now, take a look at the third one. When I increase the sample size now, okay, when I increase the sample size, that shape becomes that of a normal distribution. In statistics, the best probability distribution is normal. That's why they call it normal. Put forward by, we also call it Gaussian distribution, because when your data set follow normal distribution, inference, making judgment, making conclusion is very, very easy. And that's why. But if we have a certain probability distribution for a data set, what are we going to do to, in order for that distribution to attain normality? What it's trying to tell us? If we have a binomial distribution is not normal distribution. But what am I going to do? If I want binomial distribution to become a normal distribution, then I need to increase my sample size. And that's the central limit theorem. The more sample you take, the more you are very close to the truth. Okay, so what I'm going to do next time, I'm going to show you the derivations. I'm going to make use of the board tomorrow, where I'm going to derive. I'm going to make use of derivations. How do we derive that to be that? How do we derive that to be that? Because in this course, we're actually going to ask you a theoretical question where derive show that expected value of y equal to mp with y followed by binomial distribution, or if y follow a particular distribution. Okay, this is where I'm actually going to stop today. Is there any question before I go? Okay, make sure you stay safe and have a lovely day. Bye for now, everyone. This of you online. Is there anyone want to ask question?